In this next lesson, we're going to take a first look at trigonometry. Now, before we start, let's just do a little bit of revision. Imagine we have a right angle triangle as shown. Well, you remember from your junior cert that the hypotenuse squared, h squared, is equal to the sum of the other two sides squared. So we can write that h squared equals o squared plus a squared. And we can also relate the side lengths using the sine, cosine and tan relationship. And sine of theta is the opposite over the hypotenuse. Cos of theta is the adjacent over the hypotenuse. And tan of theta is the opposite over the adjacent. Now, another important measurement is radian or radians. So if we have a circle as shown with a radius r, then we can define 1 radian as the measure of the angle formed by the arc equal in length to the radius. So in other words, if the length of this arc is r, the same as the radius, we have rotated 1 radian. Now we can also say that in 1 revolution, the total distance that we travel would be 2 pi r, the circumference of the circle. So the number of radians in that length will be 2 pi r divided by r, which will give us 2 pi. So in 360 degrees, we rotate 2 pi radians. So let's have a look at question 1. Here we're asked to convert 225 degrees to radians. So in 1 complete revolution, 360 degrees, we have 2 pi radians. So 1 degree is 2 pi divided by 360, and 225 degrees will be 2 pi multiplied by 225 over 360. Divide 2 into 360, we get 180. Divide above and below by 5, we get 45 pi over 36. And divide above and below by 9. 9 into 36 goes 4, and 9 into 45 goes 5. So 225 degrees is 5 pi over 4 radians. In part 2, we're asked to convert 150 degrees to radians. So once again, 360 degrees is 2 pi, or 180 degrees is pi radians. So divide across by 180 to give us 1 degree, it's pi over 180. And we want 150 degrees, so 150 degrees will be 150 pi over 180. We can divide above and below by 10 here, and then divide above and below by 3. So 150 degrees, it's 5 pi over 6 radians. So here are some conversions that you could try. Convert 270 degrees to radians, 120 degrees to radians, and 315 degrees to radians. Now in question 2, we do the reverse. We want to convert degrees to radians. So in this first question, we're asked to convert 5 pi over 3 to radians. So this time we can say that in 360 degrees, we have 2 pi radians, or 2 pi is 360 degrees. That means pi radians is 180 degrees, half of 1 revolution. So 1 radian would be 180 degrees over pi, and we want 5 pi over 3 radians. So 5 pi over 3 radians would be 180 times 5 pi over 3 divided by pi. And the pi's cancel here, and 180 by 5 divided by 3 is 300 degrees. So you could try converting 7 pi over 4 to degrees. Next, let's take a look at an arc or a sector of a circle. So on page 9 of the log tables, you'll see a circle, and you'll see a sector of the circle. And if we have a sector, the angle theta here can be measured in radians or degrees. So in this case, we'll consider radians first of all. If theta is in radians, then the length of the sector here is going to be given by the following relationship, which is r times theta. So the bigger the angle, the greater the length of the arc or sector will be. The other important consideration here is the sector area. The area, again, if you refer to page 9 of the log tables, can be given as half r squared theta, where again theta is in radians. So let's take a look at question 3 here. We're told that the radius of a circle is 20 centimeters, and we're asked to find the angle subtended at the center by an arc of length 8 pi centimeters. So the best thing to do here is a neat sketch. Here we have the radius, it's 20 centimeters. We have a rotation angle theta, which we'll measure in radians, and the length of the sector or arc is given as 8 pi. So remember the relationship between L, R and theta. We can say that the length of the arc is R times theta. So in this case we know what L is and we know what R is, so we should be able to find theta. So theta is L over R. So substitute 8 pi for L and 20 for R, and we get theta is 8 pi over 20, or divide above and below by 4, it's 2 pi over 5 radians. In question 4, we're given the area of a sector of a circle, it's 50 centimeters squared, and we're told that the angle at the center is 2 pi radians, and we have to find the radius of the circle. So because we're given the area, we can use the relationship between area and rotation, and we can say the area of a sector is half r squared theta. So we know the area A, we know what theta is, so we need to find r. So let's rearrange this expression, or substitute the values first. We get A, put 50 for A, r we don't know, and theta is 2. So the 2's cancel here, so we get r squared equals 50. That means r is the square root of 50, which is, if we can write this down, it's 25 by 2. The square root of 25 is 5. So r is 5 times root 2 centimeters. Next, we consider the area of a triangle. Now you can look up page 9 and you get the important formulas relating to the area of a triangle. And you may remember from the junior cert that the area of a triangle is half the base by the perpendicular height. But in general, if we have a non-right angle triangle, as shown here, if we have an angle between two sides, we can say that the area of the triangle is half AB times the sine of the angle between the two sides. So the area of a triangle is half AB sine C. If we had the angle up here, which would say the angle B, we could say the area is half AC times the sine of the angle between A and C. And similarly, if we had this angle here, let's say it was A, we could say the area of a triangle is half BC times the sine of the angle between them, sine of A. In question 5, we're given a triangle ABC, and we're told that AB is 5, BC is 8, and the angle ABC is 47 degrees, and we're asked to calculate the area of the triangle. So it's always a good idea to make a neat sketch. So we have the distance AB is 5, and we have BC is 8. So BA is 5 and BC is 8, and we're also given the angle between 5 and 8, which is 47 degrees. So remember, the area of a triangle is half the product of the two side lengths, 5 by 8, times the sine of the angle between them. So in this case, we can say A is half A, which is 5, half 5 by 8, sine of 47, and that works out to be 4 5's 20 times the sine of 47, and if we calculate this on our calculator, we get 14.63 centimeters squared. Now earlier on we had a look at right angle triangles. What about non-right angle triangles? Well, if we have a non-right angle triangle, such as the one given here, we can relate the sides and the angles using one of two formulas or two rules. One is the sine rule and the other is the cosine rule. So let's have a look at the sine rule first of all. The sine rule states, and again this can be found on page 16 of the log tables, that the length A over the sine of the corresponding angle is equal to the ratio of any other length and its corresponding angle. So we can say A over sine of A is B over sine of B is C over sine of C. Or we could put the reciprocal of this. We could say sine A over A is sine B over B, or it's equal to sine C over C. So let's take a look at a question here, question 6. We're told a triangle ABC has the side length BC is 9 centimeters, AC is 10 centimeters, and the angle BAC is 45 degrees. And we have to find one possible value for ABC. Later on we'll see that it's possible in questions like this to have more than one value for the angle, but we'll talk about that later. So once again we need a diagram. So BC is 9 and AC is 10. So using the common C here, we can say BC is 9 and AC is 10, and the angle between BAC is 45 degrees. So remember the sine rule, take the side length and the angle. So we could put the ratio sine of A over A is sine of B over B. So in this case, the angle A is 45 degrees. So it's going to be sine of 45 over the corresponding or the opposite angle, which is our distance, which is 9, is equal to the ratio of sine of B over 10. We cross multiply and we get sine of B is 10 times sine of 45 over 9. And if we calculate this, we get 0.786. So if sine B is 0.786, B is the inverse sine of 0.786, which works out to be 52 degrees. Now let's consider the cosine rule. So once again, if we have a non-right angle triangle, we can relate the angles and distances as follows. And the sine rule states, you get this from the log tables, that a squared is b squared plus c squared minus twice bc, the cos of a. So in other words, the side we want, in this case it's a, we could say that a squared at the corresponding angle, or the angle opposite the side length is a, we could say a squared equals the sum of the other two lengths squared, b squared plus c squared, minus twice bc times the cosine of the angle between them. So, for example, let's say we wanted b, so we could say b squared, the angle opposite is b, so b squared in this case would be c squared plus a squared, or a squared plus c squared, minus twice AC times the cosine of the angle between them, which is the angle B. So here in question 7, we're given a triangle DEF. We're told DE is 4, DF is 6, and EF is 9. And we have to calculate the measure of the largest angle. So once again, we do a sketch, which is essential. We have FE is 9, FD is 6, and ED is 4. So we've no angles, and usually when we've no angles, we can't use the sine rule. We usually use the cosine rule. So we want to measure the angle of the largest angle. So the largest angle will be the angle opposite the largest side length, which is 9. So we want to get this angle here. So remember, the side opposite the angle squared. So in our case, we'll write 9 squared equals the sum of the other two lengths squared, 6 squared plus 4 squared, minus twice 6 by 4 times the cosine of this angle here, cosine D. So we can write it like this as follow. A squared equals b squared plus c squared minus twice bc cos of the angle, cos of A. But in this case, we're looking for 9. We're looking for the angle opposite 9. So it'll be 9 squared equals 6 squared plus 4 squared minus twice 6 by 4 times the cos of the angle between 6 and 4, which is cosine D. So we can work this out. We get 81, 6 sixes are 36, 4 squared is 16, 2 fours are 8, 8 sixes are 48. And bring everything to one side, we get 81 minus 52, which is 29, equals minus 48 cosine D. Divide across by minus 48, we get cos of D is minus 29 over 48, which is minus 0.6042. So we have cos of D equals minus 0.6042. So D will be the inverse cos of 0.6 or minus 0.6042. And if you look this up on your calculator, you'll find that D is approximately 127 degrees. Now in the next question, question 8, we're given a diagram and some dimensions, and we're asked to find the angle P or Q and the side length PS. Now you'll see when we look at this question a bit more deeply that we'll use a combination of the sine and the cosine rule. So we're trying to find this angle P or Q. So we could consider the sine rule. You could say sine of this angle over 7 equals the sine of R over 5. But we have no angles, so the sine rule isn't going to work there. So what about the cosine rule? Well, we could say the side opposite the angle we want, which is this angle here, angle R if you like. So we could say 5 squared equals twice 8 by 7 times the cosine of the angle between them. And we'd be left with just one angle, so we should be able to solve that. So let's try the cosine rule on the triangle PRQ. So the sine, as I said, the cosine rule will be the side opposite the angle squared. So 25 squared equals the 8 squared plus 7 squared minus twice 8 by 7 times the cosine of the angle between them, which we'll call R. So 25 equals 64 plus 49 minus 112 times cos of R. Add 49 to 64 and take it from 25. We get minus 88 and multiply it across by minus 1 and we'll get 112 cos of R equals 88. So that means that the cosine of the angle R is 0.7857. So R is the inverse cos of this angle, which is approximately 38.2 degrees. So now let's look at calculating the length of PS. Well, if we look at this time, we look at the triangle RSP, and we see we do have an angle on the side. So we could use the sine rule. We could say sine of 30 over 7 is the sine of this angle here over PS. But we don't know this angle here. But what we do know is we could subtract it from 180, 38.2 from 180 to get it. So let's calculate the angle R here by, it's going to be 180 minus 38.2, which is 104.8. So now we have this angle, with two angles in the triangle, so we could say sine of 30 over 7 to sine of 141.8 over PS. So we can say sine, as I said, sine of 141.8 over PS is equal to the sine of 30 over 7. So cross multiply, we get 7 times sine of 141.8 over sine of 30 is equal to PS. So if you work this out in your calculator, it works out at 8.7 centimeters. So the length PS is 8.7 centimeters. So now finally in this video, let's take a look at this question, which is a bit more abstract. We're given a diagram as shown here. You can see it's a right angle triangle at S, and we have a distance Q here is a distance 10 centimeters from R, and we're trying to find H here. It could be the height of pole or mast or something like that. So let's have a look. Here are two hints that might help you to do this question. The first one is to consider which length is common to both of these triangles. So you can see you have a triangle QRS or PQR, and you have a triangle PRS, and the distance or the length PR is common to both of those. So maybe we could call that length or PRX. And the other thing you could do is you notice you have two internal angles here, B and C, and an external A. And if you remember from your geometry, the value of the external angle is the sum of the two internal angles. So A equals B plus C. So if A equals B plus C, that means that C is B or A minus B, because if you look at this expression H, there's no C in it. So it's best to have C in terms of A and B. And you can see there's an A minus B here at the bottom. Okay, so if we consider this triangle here, Q or P first, we could use because we have a side length here, we could use the sine rule. So we could say the sine of B, so the sine of B over X is equal to the sine of C over 10. But we know C is A minus B, so that's the same as sine of A minus B over 10. So if you look at this expression, we could find X, remember it's a common length between the two triangles. So X, we could cross multiply here and we get X equals 10 times sine of B over sine of A minus B. And that's beginning to look like this expression up here. It's not far off. So now let's look at the bigger triangle here, or well, the other triangle, PRS. This is a right angle triangle, so we don't have to bother with the sine or the cosine rule. We could just say sine of A is H over X. So we can say sine of A is H over X. So that means that x is h over sine of a. So we have x from the triangle PRS, and we have x from the triangle PQR. So x must be the same in each case, so we could write this expression here equal to h over sine of a. And remember, we're trying to find h, and you can look at what we're trying to prove. Cross multiply, you get h equals 10 times sine of a sine of b over sine of a minus b, which is what we were asked to prove. So it doesn't look as difficult as it might have been at the beginning. So remember, you have two triangles. You get the key here really was to see that the PR is common to both of those triangles. So get an expression for PR in this triangle on the left and an expression on the right, equate them, and you should be able to work out what h is.